Hi and welcome everyone. In this lecture, I want to go over inner product spaces. So now before to see what inner product spaces are, it's a good idea to review the dot product. We have seen the dot product before. Again, u dot v, that's the dot product. When you do that, it's u1 v1 plus u2 v2 plus dot 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 un vn. These are the components of those two vectors. So you multiply the corresponding components and you add them, and it's a scalar. The properties u dot v can be written as magnitude of u times magnitude of u times cosine theta, and that's how you can find the angle between the two vectors. U dot u is the same as magnitude of u squared. U dot v equals to 0 if u is perpendicular or orthogonal to v. U dot v is the same as v dot u, that's the commutative property. Then we have the distributive property, u dot v plus w is the same as u dot v plus u dot w, and c times u dot v can be written as cu dot v or u dot cv. U dot u is the norm of u squared, or the magnitude of u squared, and it's always greater or equal to 0. And u dot u equals to 0 if and only if we deal with the 0 vector. Now the inner product. First of all, the notation, please be careful. So you do use angle brackets, and you write it as u comma v, and be careful, these are not the components, these are vectors. Or sometimes in some books you're going to see u and just a line v with angle brackets. I do use that one in my lectures. So now u and v are vectors in a vector space, and c is a scalar, just like before. Any inner product on V satisfies the following axioms. So for inner product spaces, you have to check 4 axioms if you want to prove that the function is an inner product. For vector spaces, we did use 10 axioms, but in this case it's 4 axioms, and then we'll see how they're used. First of all, the commutative, so property u inner product v should be the same as v inner product u. U inner product v plus w should be the same as u inner product v plus u inner product w. C times u inner product v should be written, can be written also as c inner product v, or u inner product cv. Cu inner product v or u inner product cv. U inner product u has to be greater than 0, and u inner product u is 0 if and only if u is 0. So let's see how this works. The first example I took is just the dot product. So show that the dot product in Rn satisfies the 4 axioms of an inner product. So we have a vector, and again here I did put the components of u and a vector v, and these are the components. There is no line arrows on top, so these are the components of v. By definition, we know u dot v is the sum I starting from 1 to n ui times vi. So u dot v is the same thing as the sum ui vi, and that's the same thing as the sum vi times ui. So the commutative property works. U dot v is the same as v dot u. This property, you can easily show it by, again, using the components or the summation notation. U dot v, that's pretty long, but please try it. We have seen this a lot in our last lectures. Use the components, and then you'll see u dot v plus w will be the same as u dot w plus u dot v plus u dot w. And then again, if you use the components of these two vectors, c times u dot v is the same thing as cu times the dot v, and it's the same thing as u dot cv. So this is gonna be satisfied. Just putting a c here and then showing with the components. U dot u is norm of u squared. That's always positive. And if you deal with zero vector, u dot u is going to be 0 if and only if u is 0. So what's the conclusion? The conclusion is dot product is an inner product. We first learn dot product because it's just easier to see, but then in reality dot product is an inner product because it's all the four axioms are satisfied with the dot product. Let's do an example here. You're given two vectors, u with the components u1, u2, this is in R2, and v with the components v1, v2. Now, if we do, you're given this function, so defined as u inner product v is u1 v1 plus 2 times u2 v2, and that's a question if that's an inner product. So start one by one, then let's check those axioms. U inner product, if it's an inner product, in this case let's just call it inner product. U inner product v is u1 v1 plus 2 u2 v2. We know that u1 v1 can be written as v1 times u1, and here u2 times v2 can be written as v1 v2 times, let me change that, v2 u2, so you can change the places, and then when you do that, that becomes v inner product u. So the first axiom is satisfied. Then you can say let w equals to w1 w2 with its component. Let's try this one, u inner product v plus w. That you can write that as, you just follow what we have, what's given here. So here is u1 times v1, but in this case it's going to be u1 times the component of that vector, which is v1 plus w, and 2 times u2 times v2 plus w. Now this becomes u1 v1 plus u1 w1, and that's very obvious, 2 times u2 v2 plus 2 times u2 w2. Now if we arrange that, we can put these two together, so which is right here, that's u1 v1 plus 2 times u2 v2, and we can take those two, u and w, and put it here together. So if I just show the parentheses here, what this is u inner product v plus u inner product w. So the distributive property works. Axiom number 3, if we have c a scalar, so I just want you to note that c times u is c times u1 v1, and c times v is c times v1 v2. So c inner product uv, you can write that as, just using that definition given in the problem, c times u1 v1 plus 2 times u2 v2. Distribute, you get cu1 v1, and that's plus 2 times cu2 v2. So that's the same thing as saying it's c u inner product v plus, and that's the same thing as u inner product cv. So that works also. If we take one of the vectors, v inner product v, it's going to be, so V1 times V1, which is V1 squared. Again, we're always using this definition. So if the components, if it's just only one vector, it's going to be V1 times V1, which is V1 squared. And 2 times V1 is V2 times V2 is V2 squared. That's squared and that's squared, and there's a positive sign, so this quantity is always positive. U inner product V, if U equals to 0, that will be 0 and that will be 0. So it's going to be 0 or vice versa. If and only if V, U equals to 0, V equals to 0. So all the 4 axioms are satisfied. So this is an inner product. So let's do another example in R3. You have U with its components and V with its components, and that's the defined function. So it's U1 V1 minus 2 times U2 V2 plus U3 times V3. We want to know if this is an inner product. However, you can directly jump to axiom 4. Axiom 4, if our vector is U, if you take, for example, that vector with the components 1, 2, and 1, U inner product U is going to be 1 times 1 minus 2 times 2 times 2 plus 1 times 1. And guess what? That is negative, and we can't have that because the axiom that is satisfied U inner product U has to be positive. So you can just stop right there and you're going to say not an inner product. Now, inner product spaces, they can use with different vector spaces. In this case, another example, the M 2x2 matrices. So you're given couple of 2x2 matrices, and the function is defined as A inner product B is A11 B11 plus A12 B12 plus A21 B21 plus A22 B22. And the question is if this is an inner product. So the first axiom is pretty straightforward. Just write those and these are just numbers. You can switch them. So A inner product B will be equal to B inner product U. Take your time and please do those so you can see it on your own. You can take a third matrix and then see if A inner product B plus W is the same thing as A inner product B plus A inner product W. These also can work. Use this function and substitute. Again, these are pretty wrong then, but you can, they're going to be satisfied. C times A inner product B will be equal to CA inner product B and will be equal to A inner product CB. Always use the entries and the defined function, and you'll see this will work. So if I take one of those matrices, B inner product B, in this case is going to be B1 times B11 times B11, which is B11 squared, B12 times B12, which is B12 squared, B21 times B21, which is B21 squared, and B22 times B22, which is B22 squared. And as you notice, these are all squared, so it's positive. And if you take the 0 matrix, B inner product B is going to be 0 if B is the 0 matrix where all the entries are 0. So this is an inner product. So basically any function, you first see how the inner product is defined. or if it's an inner product. And you check this for axiom. If they're satisfied, then you can say it's an inner product. Let's do another one. F and G are continuous functions on this interval. So, or you can just say that C, A, B. The inner product is defined as, this is calculus, the integral going from A to B, f of x, g of x, dx. So question mark, well, let's see if that defines as an inner product. Let's do the first one. F inner product G, write the definition. We have that. We know when we have the integral, we can just put g of x first and then f of x. We're just multiplying the functions. So you get g inner product f. So the first one is satisfied. F inner product g plus h is f of x. And again, instead of the second function, you just put g of x plus h of x. And we know with integrals, you can separate them. So this is f of x, g of x dx plus the integral going from a to b f of x and h of x dx. So let's change that to h of x dx. So basically, that becomes f inner product g plus f inner product h. So distributive property works. If we put c in front, c inner product fg, so with integrals you can put the c in the front, or you can take, if it's a constant inside the integral, it's the same thing, you're going to end up with the same answer, and that can be written as cf inner product g. And if you show one of them, that's good enough. You can also say that equals to f inner product cg. The inner product of the function by itself, that's f and f, so it's going to be f of x squared. We know that's an area and that's a positive function, so the area will be above the x-axis, so it's positive. Therefore, so it works. Sometimes I put greater than 0, greater than or equal to 0, but then it's okay, you can show that case. And the f inner product f is 0 if and only if we're dealing with the 0 function. So these are all satisfied, so this is inner product. With function is the same way. You just have to be careful what they defined as the inner product, if it's an inner product, or you follow here, you have two polynomials, so p of x and q of x, and they said, the problem says the inner product function is the a0 times b0 and a1 times b1 and dot 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 plus an times bn. Here I didn't do this, but that can be an example. Please double check this example yourself and go over the 4 axioms, see if it's going to work, then it will work. The answer is going to be yes, but try it yourself. Again, you just have to be patient and use those coefficients one by one, write them, and you'll see them. Now the length, distance, and angle. If u and v, well, let u and v be vectors. So in an inner product space, the length or the norm of that is just to remember this, remember the dot product. With dot product, we said this u dot u, but in this case, it's going to be u square root of u inner product u. The distance between u and v is just can be written as norm of u minus v. The angle between them, it's exactly like the dot product, but here it's going to be the inner product. So cosine theta is u inner product v divided by norm of u times norm of v, or the magnitude of v, u times magnitude of v. And if u inner product v is 0, then u and v are orthogonal. So this works with different cases. If you're not in R2 and you're dealing with different vector spaces. Also, if the norm of u or the magnitude of u is 1, then u is a unit vector. If v is any non-zero vector in an inner product space v, and again, this is the vector space v, then the vector u v over norm of u is the unit vector in the direction of v. I'll do some examples. You'll see how they're similar in different vector spaces. And again, cosine theta, I went over that, is u inner product v divided by norm of u times norm of v. And again, it's cosine, so it's always between -1 and 1. Let's do an example. This one I did it with a polynomial or with polynomials. So you're given the polynomials. So these are the polynomials, R of x. And it says the function is defined by a0, b0, a1, b1, plus dot 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 plus an, bn. So you are given three polynomials. The first one is 1 minus 2x squared. The second one is q of x is 4 minus 2x plus x squared. And r of x is x plus 2x squared. If you want to find p inner product q, so you just follow. Here it says a0, b0, the constant term of p and the constant term of q. So it's right here, 1 times 4. Then the linear term of p and the linear term of q here, there is no linear term or the term with x, so it's going to be -2 times 0. And finally, the quadratic coefficients. So here is 2 and here is 1. Here is -2 actually, so it's -2 times 1. If you calculate that, that's what you get. The inner product of q and r, again, the constant term of q is 4, it's right here. And the constant term of r, there is none, so it's 0. So that's the first one. Plus, then the linear term of q is -2, it's right here. The linear term of, or the coefficient of the linear terms, here it's 1, so it's -2 times 1, plus the quadratic coefficient or the term, the coefficient of the quadratic term, here is 1 and here is 2, so it's 1 times 2, and if you do that, you get 0. So it's pretty simple to calculate the inner product and get the number. If we want the norm of q, the norm of q is just inner product q by itself. So it's going to be the constant 4 times 4, and that's going to be, and it's square root of that. So we should put the square root here. So it's 4 times 4 plus -2 times -2, and then plus 1 times 1, which is the coefficient of that term. And if you do that, that's what you get. You calculate, you get square root of 21. We want to find the distance between p and q, so we use the same definition of the distance between two vectors. So it's going to be the norm of p minus q. For this one, first find p minus q. That was our p and that was our q. So if you subtract them, you get this polynomial, and you just find the norm of that polynomial, which is going to be square root of p minus q inner product p minus q, which is going to be -3 times -3 plus 2 times 2 plus -3 times -3. Again, we use those coefficients, and if you do that, you get square root of 22. And that, let me write that for you also. So this is just the inner product of P minus Q and P minus Q. First find P minus Q, then apply it. So another example with functions. So this is, again, that's calculus. Let's say f of x equals to x and g of x is x squared. And it's between 0 and 1. So the inner product is defined as so if we define the inner product, we can say, let me write it. It's going to be the integral going from 0 to 1 f of x g of x dx. So now the norm of f, or the magnitude of f, is just square root of the inner product of f with itself. So you take this function and then put f of x substitute. So that's just going to be square root of integral going from 0 to 1 of x times x, which is x squared. So you get x cubed over 3, and that's going to give you square root of 1/3, or 1 over square root of 3, or square root of 3 over 3. The distance between f and g, that's going to be the norm of f of x minus g of x. F of x minus g of x, we want the norm of that. So again, it's just the square root of the inner product x minus x squared and x minus x squared. And by definition, that was defined by the integral of that function. So you write that, you can expand that and take the integral, substitute. This is a simple calculus 1 problem, and substitute the limits. And if you do that, you get those numbers. And if you do some little arithmetic, you get 1 over square root of 30, or square root of 30 over 30. I think that's good enough for this lecture. Please watch this couple of times to calculate them. It's not hard. Learn how to prove inner products. If any of those 4 axioms doesn't work, then you stop right there and say it's not an inner product. Then if it's working, then you can find the norm, the distances, as I did, and it works the same for different vector spaces. Thank you for watching, and in the next videos we're going to see how we can use the inner product. Have a good one, everyone, and I'll see you in my next video.